Hello, I'm Brian Young. Today we're going to do Module 26211, Control Systems and Fundamental Concepts. Let's get started. Module 26211, Control Systems and Fundamental Concepts. Successful completion of this module prepares you to identify and explain how to wire magnetic and mechanically held contactors, identify and explain how to troubleshoot various relays, describe low voltage lighting control systems and their installation requirements. And then there will be a performance task that your instructor wants you to do. Overview: contactors are used to make and break the electrical circuit serving high current loads, such as motors. However, when used in most motor circuits, motor overload protection must be added to create what's known as a motor starter. Relays and electromagnetic devices that are used to provide additional control over motor starters, contactors, solenoids, timers, other low current loads. This module describes the operation principles of contactors, motor starters, and relays, and explains how to install and troubleshoot simple control circuits. So a relay is an electrical solenoid. It's going to move a plunger, and that plunger is going to have contacts attached to it, so you can change the state of the contacts. You can make normally open contacts closed, and you can make normally closed contacts open. That basically is what it is. We'll see in just a minute here. It's magnetic mechanically held contactors. Describe contactor and relays and how they're applied in lighting circuits. Explain how to complete forward and reverse motor contactor connections. Explain how to select mechanically held contactors. Contactor is an electromagnetic control device that's designed to handle relatively high currents. The traditional contactor is identical in appearance, construction, and current carrying ability to the equivalent National Electro Manufacturers Association magnetic motor starter. Magnetic assembly, the coils, the contacts, the holding circuit interlock, and other structural features are basically the same. Now, here's a highlight. It says the primary difference is that a contactor does not provide inherent overload protection, while a complete motor starter does. In order to be considered a motor starter, you have to have overload protection to protect the motor coils. All right. Contactors are used alone to make or break electrical circuit to high current resistive loads and some high current inductive loads. Make or break: make means to close a set of open electrical contacts so that electricity can flow through them. Break is to open them, open a set of closed contacts. This is a typical magnetic motor contactor. Contains a coil of wire wound around an iron core and an armature. The coil acts as an electromagnet. When the proper electric current is applied, it pulls the armature towards it. Since the movable electrical contacts are attached to the armature, when the armature moves toward the coil, movable contacts follow. So here's the coil. It literally is a coil of wire. And when you put a current through it, it becomes an electromagnet. That electromagnet attracts the movable core. It's like an iron T made out of laminated iron or steel, and it'll pull down on it. When it does, these movable contacts are going to make contact with these stationary contacts below. It'll seal these contacts, or it'll make, we're talking about make and break, it's going to make them. It's going to seal them. We will have electricity flowing through them. So we could control a 480 volt motor, three-phase motor, with 120 volts single phase. This coil probably operates on 120. And here's a contactor coil armature structure. This is more of a diagram. So here's your movable, this is the stationary core, and this is the movable core. And when we put current through these windings, this coil, this movable core will be drawn toward this electromagnet. This core will become magnetic, and it'll pull down on this, actually up the way they've got it drawn. That'll allow these movable contacts to move into place up above, making contact with some stationary contacts. And it goes on to describe it. It says that when power is applied to the coil, the contactor is said to be energized. When no power is applied, it's said to be de-energized. The de-energized position is also called the normal position. The contacts are in their normal state when they are not, when the contactor is not energized. So if we talk about normally open contacts, we talk about off the shelf, out of the box, in your hand. If those contacts are open, they're not making contact, they're open, normally open. If you take the contactor off the shelf, out of the box, in your hand, and those contacts are touching and they're making contact, those are normally closed. In its de-energized state, that is the normal position. Normally open, normally closed. So when the coil is de-energized, one or more springs returns the armature to its original position. All sets of contacts then revert to their normal de-energized position. So here they're talking about normally closed contacts, a set of electrical contacts that are closed when the enclosing relay or contactor is de-energized. Normally open, a set of electrical contacts that are open when the enclosing relay or contactor is de-energized. That's their normal state. Notice that a shading coil is shown in the iron core in figure 2. There's a highlight that says shading coils are used with AC relays to prevent contact chatter and audible hum. A shorted turn of wire that surrounds a portion of the pole of an AC electromagnet and produces a delay in the change of the magnetic field in that portion. This serves to prevent chattering, contacts, and reduce audible hum. So here is that shading coil. It's just one closed loop of conducting material. And because we have a changing electromagnetic field in this coil, that changing magnetic field is going to induce a secondary voltage and current in this shading coil. It's inductive, it's induced, so it's 90 degrees out of phase with the magnetic field that induced it. So when our sine wave, let me see if I can do this here. Our sine wave, and they're showing me in reverse, so I'm not sure what I'm doing. I want to make sure I do it right with you. Here's the sine wave, and 120 times a second, twice a cycle, the voltage drops to 0, which means the magnetic field in this coil is shut off, which would allow this spring to start to open these contacts, and then it immediately would start flowing again right afterward. As soon as it crosses the x-axis, as soon as that sine wave turns from one amplitude to start the second amplitude, that magnetic field will be returned, and the movable coil, the movable core, will slam shut. So 120 times a second, this thing tries to open because of the spring, and it returns to a shut position because of the magnetic field. Well, this shading coil provides a 90-degree lag in that. There's a tiny little residual magnetic field around this shading coil that holds that contactor in place during those 0-volt moments. When the voltage falls to 0 and the magnetic field around the coil starts to collapse, that shading coil has residual magnetism that keeps those contacts closed. It reduces the coil chatter, the relay chatter. So it's not perfect. You still get a slight hum, but it's a lot quieter than it would be without the shading poles. If you ever have a contactor that's making a lot of noise, check to see if the shading coils have been broken. Nothing lasts forever. They could break, and because of that, you can get a lot of chatter. All right. So here's a highlight. Oh, I already read this. The shading coils are used with AC relays to prevent contact chatter and audible hum. They function the same way as they do in a shaded pole motor. In general, a shading coil provides a continuous magnetic flow to the armature when the voltage of the AC waveform is 0. So, electromechanical relays operate on the solenoid principle like contactors. This means that they convert electrical energy into a linear motion. In this example, a coil of wire is around an iron core. When the current flows through the coil, magnetic fields developed around the iron core. The magnetic field of the iron core attracts the armature, pulling it toward the coil. When the armature moves, the movable contacts make or break a connection with a stationary coil. Wow. This is a closed relay or an electromagnetic relay, electronic relay. But all right. This is a smaller relay, and they actually have two position switches. This contact is going to make position with two different contacts. So when it's de-energized, this upper contact is normally closed, and this lower contact is normally open. When we energize this relay, those two contacts change state. The normally closed contact opens, and the normally open contact closes. So you can actually use them for two separate things, normally open, normally closed. All right. Figure 4, the relay is shown de-energized. The movable contact is touching the upper stationary contact. This contact set is normally closed. When the relay coil is energized and the armature moves toward it, the movable contact breaks the connection with the normally closed stationary contact and makes the connection with the normally open stationary contact below it. Wiring diagram, the movable contact would be the common terminal. The stationary contact terminals would be labeled as normally open, normally closed. All right. They're talking about, they're saying a relay with a set of two stationary contacts, one movable contact that operates this way is called a single pole double throw relay. Single pole double throw, SPDP. This is an example of a single pole double throw relay. So here's a highlight. It says filament type lamps, tungsten infrared quartz, have an inrush current approximately 15 to 17 times greater than their normal operating current. Those filaments have to heat up and increase their resistance in order to lower the amount of current going through them. So when they're cold and you first turn them on, there's an inrush of an incredible amount of current. And the contacts have to be able to take that. And the lighting relay has to be built to withstand that inrush current. So here's table 1, electrical ratings of AC magnetic contactors and starters. Here's this column, tungsten and infrared lamp load amps, 250 volts maximum. Tungsten and infrared lamps. Then they talk about different size NEMA contactors. This is a 00 or a 2 watt NEMA starter or contactor, and it's small. So at 230 volts, it's good for 5 amps on the contacts. That same 230 volt at 1 aught is good for 10 amps. And at a number 1, it's good for 15 amps. Here's a single pole 230. It's good for, it's actually a rated a size 2, but it's single phase, not 3-phase, and it's only good for 24 amps. Now the 230 volt polyphase number 2 starter or contactor is good for 30 amps. All right, that's highlighted. And then they have another chart here. I don't have any highlights in this chart that I know of, so I'm not going to worry about it. It says unlike standard contactors, lighting contactors not rated in horsepower or categorized by NEMA size. They're categorized by their amp rating. Note that the delicate lighting contactors are specialized and should not be used to control motor loads. Basic circuit using a lighting contactor to control a high current lamp is shown in figure 5. So here you have your power supply, and we have 2 normally closed stop buttons and 2 normally open start buttons in parallel. So when we push this normally open start button, it energizes this relay closes this normally open R1 relay. This set of contacts closes. And The starting current can bypass the start buttons and feed the relay directly. So now these are momentary switches. You can let go of it and it'll open, but the lights will stay on until we push one of these normally closed stop buttons to turn it off. It comes through this lamp, and here's this R1. This is the second set of contacts on relay R1. So here's the first set of contacts on relay R1, normally open. Here's the second set of contacts on relay R1, normally open. All right. And they go to show us what we can do for emergency lights. Um, we have AC power, and that AC power is being rectified by a diode, so it's keeping this battery charged. And while we have energy, this relay is energized. This normally closed contact is open, so the emergency lamp is not lit during normal operating circumstances. When we lose power, this relay is de-energized and this normally closed contact closes because the relay is not energized, keeping it open. So it closes, and now, since there's no AC, the battery can feed this emergency lamp through this small part of the circuit right here. So when the power is on, the battery's being charged and the light is not lit. And when the power is disconnected, then the battery makes the emergency lamp light up. All right. Let's see here. It says figure 7 shows a diagram of lighting contactor controlled by a single pole switch. The contactor has 6 sets of contacts, each of which controls the power to one of the 6 lighting circuits. So here we're multiplying how many lights we can control with this one circuit by using a contactor. So each one of these circuits, depending on what it's controlling, can be separately fed from a different circuit breaker. They're saying it's a 200-watt lamp. Maybe we've got 1,500 watts on this circuit, 1,500 watts on this circuit, this circuit, this circuit. We can control all 6 of them at the same time with this one single pole switch by using a contactor, a lighting contactor. So, forward and reversing motor contactor connections. So, we're going to talk about a 3-phase motor. We can reverse the direction of this 3-phase motor by switching any 2 leads. If we swapped 1 and 2, we would reverse this motor. If we swapped 2 and 3, we would reverse the motor. Or if we swapped 1 and 3, we would reverse the motor. It's kind of an industry standard to swap 1 and 3 and leave 2 alone. So that's what they're doing. They have forward where L1 is controlling T1. So line 1 is controlling the T lead to the motor 1, and line 2 is controlling the T lead 2 to the motor, and line 3 is controlling the T lead T3 to the motor. So when the forward contactor is energized, A, B, C, line 1 feeds T1, line 2 feeds T2, line 3 feeds T3. When we reverse the motor, when we energize the reversing contactor, look what happens. Line 1 now feeds T3. Line 2 still feeds T2. Line 3 is going to feed T1 because these reversing contactors are closed. These contacts are closed and the forward contacts are open. If we happen to have the forward contactor and the reversing contactor energized at the same time, that would be very bad because we'd have a dead short between lines 1 and 3. You see here that we'd have line 1 coming to line 3. If these contacts were closed at the same time as these contacts, it would be a dead short. So the forward contactor is de-energized, the second contactor can be energized, closing its contacts R, which reconnects the line to the motor in a different configuration. Note that by running through the reverse contact, line 1 is now connected to motor terminal T3, and line 3 is connected to motor terminal T1. The motor will now run in the opposite direction. All right. Manual reversing starters are mechanically interlocked. That's a highlight. Manual reversing starters can also be used as as in the magnetic version, the forward and reversing switching mechanisms are mechanically interlocked, but electrical interlocks are not provided. All right. Mechanically held contactors. Sometimes you want to use a mechanically held contactor. You'll only momentarily energize the latching coil to close it or the unlatching coil to open it. And for the rest of the time, the power is not turned on. It's just momentary. It says in a conventional contactor, current flows through the coil, creates the magnetic field to attract the armature and close the contacts. Any normally open contacts will close while any normally closed contacts will open. Because the action is dependent on current flow through the coil, the contactor may be described as electrically held. When the coil is de-energized, the contacts will revert to their initial position. Versions of a mechanically held relay, it's a relay whose position is maintained by the actuation of a mechanical part or physically maintain the position, even after it's de-energized. The mechanical part or latch is disabled when an unlatched coil is momentarily energized. So the contactors are also used in some applications. The action is accomplished using two coils and a latching mechanism. Energizing one coil called the latch coil through a momentary signal causes the contacts to switch, and the mechanical latch holds the contacts in its position even after the initializing signal is removed. The coil is then de-energized while the contactor remains in position. To restore the contacts to their initial position, a second coil, called the unlatching coil, is momentarily energized. This releases the contactor, allowing it to open. You'll use these in places where you want quiet because these contactors hum. They make a lot of noise. So mechanically held relays and contactors used where the hum of an electrically held device would be unwelcome, such as auditoriums, hospitals, churches, libraries. Anywhere you want it to be quiet, you'd use a mechanically latched contactor as opposed to an electrically latched contactor or electrically energized. Due to the extreme inrush current, the maximum tungsten or infrared load current for an emphasized zero magnetic contactor is, you can go back and look and see which one that was. A manual reversing starter uses what kind of interlock? And mechanically held relays would most likely be used in what kind of a place where we want it to be quiet? All right. I'll go on to the second